Hey guys, you're watching Python tutorials on my YouTube channel Python for Microscopists. In the last tutorial, we looked at binary classification and we briefly looked at accuracy values, but that doesn't tell a lot about how good the model is performing. So the two primary things I would say that can be useful in shedding a bit more light in terms of how good the model is performing are confusion matrix and ROC curves. And the area under ROC curve is called area under the curve, AUC. Okay, so let's actually look at these, what they are first, and then jump into the code to have a look at how to code this, first of all, and then understand how well our model is actually performing. So first of all, let's understand the confusion matrix, but I should mention we are looking at this for binary classification, and confusion matrix can be actually plotted for multi-class type of data, but ROC curves typically apply only for binary classification. You can kind of use them for multi-class, but that's a different discussion altogether. Okay, so focusing on binary class, and again, let's actually look at the logistic regression curve, which basically uses sigmoid function for classification. And the reason I'm using this to illustrate this example is even in neural networks for binary classification, the last activation function you're going to use is sigmoid function typically. And so this would be very relatable. And how does a sigmoid function actually work? Well, as the name suggests, the shape of this is like a sigmoid or S-shaped. And on the x-axis, you have some sort of a feature that you're plotting, and on the y-axis, you have a probability. And why probability? Because the sigmoid function actually outputs a probability with values between 0 and 1. Now, let's say you have this type of curve, and your data points are lying here, and these data points are easy. These belong to a value of 0. In our example, we assigned that to infected. And a value of 1, we assign that to uninfected. Okay, if you want, you can switch it, but this is the convention we are going to stick with for this example. Okay, now you can say anything that has a value of probability of 0 is assigned to infected. Okay, or value close to 0 is assigned to infected. Anything that's close to 1 is assigned to uninfected. So these data points are very easy. Now, what to do with something that has a probability of 0.3? How do you assign that, right? So as you can see from this graph, we set a threshold value of 0.5, which means if you just look at where this data point lies, it actually lies inside this infected region. So I'm going to assign this to infected. What if you have something that has a threshold value of 0.8? Well, that actually lies in this above region. So as you move the threshold, for example, if I set my threshold to 0.3, something that has a value of 0.4, I mean a data point that lies like right here, it actually belongs to the uninfected class, right? Again, this is the classic sigmoid function. The reason I'm showing you this is the data sometimes, for example, in this case, the image looks like, okay, it is infected, but it can be misclassified as uninfected. Okay, so think of your uninfected as positive and infected as negative. I mean, think of for now. Okay, uninfected has a value of 1, so it's positive. So a true positive would be an uninfected image, or an image that's labeled as uninfected, and our model correctly labels it as uninfected. So that's true positive. A true negative is an image that's labeled as infected, and our model correctly labels it as infected. That's true negative. A false positive is an image that's why am I talking? I should show you this screen. This is what confusion matrix actually is, right? So these are actual values on the x, on the along the columns. These are predicted values. Okay, so uninfected correctly labeled as uninfected, true positive. Uninfected falsely labeled as infected, false negative. Infected wrongly labeled as uninfected, false positive, and true negative I just explained. Infected correctly labeled as infected is true negative. We want zeros here and zeros at the bottom, right? Anything that's false, we want zeros. Anything that's true, we want how many of our data points are assigned to that, we want those numbers assigned here in an ideal case. But That completely depends on the threshold that we set, right? So if I go back to the previous image, if I move the threshold to this point, then some of these data points lying here are now reclassified as uninfected. So what is the correct threshold point? Because what sigmoid function is giving us is a probability. We are converting that into some sort of a threshold. So what is the right threshold value? So this is where ROC curves will become very useful. I just you can pause the screen to note these down, but these are some other metrics that people use to kind of quantify the model's performance. So accuracy is something we have already done, right? Which is nothing but true positive plus true negative. It's basically this plus this, which is all the correct classifications divided by the total number of data points, right? So this is accuracy. And recall, precision, F-score, specificity, you can read this and and you can spend some time trying to understand that, but let's go ahead and try to understand ROC. First of all, it stands for Receiver Operating Characteristic. No idea why. Well, I have some idea why, because it is an adaptation from other technique, not just from deep learning, okay? So it's Receiver Operating Characteristic. And typically the graph looks like this, okay? On the x-axis, you have false positive rate. Again, you saw false positives here, except in this case, it's false positive rate, okay? And on the y-axis, you have true positive rate, which means it goes from 0 to 1. These are not hard numbers. This is basically the rate. Now, and this red line going from diagonal to diagonal, it represents random classifier. What does that mean? If you take an image and then flip a coin, and if it's heads, it is positive. If it's tails, it's negative. So this line indicates that random classifier, which is our coin telling us heads or tails. So if you do that heads or tails on all your images, this is how your ROC curve is going to look like. But if you start classifying it a little bit more carefully, then you start to move towards the top left corner. And if it is completely like this is a perfect classifier. The first time I looked at this, I did not understand this. So to make sure you don't get confused just like I did, I added a few slides to explain this. Okay, so let's go through this carefully. Here, again, I'm plotting my threshold on the x-axis, which means anything above 0.5 all the way to 1, these are all true positives, right? So everything that's closer to 1 is all positive, and all the true negatives are below 0.5. So if my data is spread this way, where all my positives are inside above threshold 0.5 and all my negatives are below, then our life is easy. Then set the threshold at 0.5, you're all set. So how does the ROC curve look like? Well, how many false positives do we have? These are all true positives. We have no false positives, which means we have 0 false positives. So look at that line, that red line. This is coming from 0 false positives, okay? And then now look at true positive rate, TPR. How many true positives do we have? All of them are true positive. That's why there is a line going horizontally at 1. That's why this is the perfect, represents the perfect classifier. So if you look at the area underneath the curve, what is the area of a box that has a size 1, of a square of size 1? It is 1, right? So my area underneath the curve is 1, which means I have 100% chance that the model will be able to distinguish between true positive and true negative. That's what AUC stands for. Now, let's start overlapping this. Some of my data is below, some of my positive data, okay, has threshold, has a value below 0.5, let's say, comes with a threshold below 0.5, which means it's going to classify them as false negatives. Exactly opposite for this negative data, okay? So my curve, ROC curve is not perfect anymore. Now it starts to come slowly inside. And now when you look at the area underneath the curve, it's not 1 anymore or 100% anymore. It's 0.8, which means if I use this model, I have an 80% chance that the model will be able to distinguish between these two. Okay, that's what this AUC is. I hope this puts things in perspective for you guys. Now, let's say both overlap, meaning we cannot distinguish between positive and negative anymore. all the data is all over the place. Okay, so our model is so crappy that we cannot kind of everything is false positive. There's an equal chance for false positive, equal chance for false negative, and true positive, right? So what happens if you have an equal chance of true positive rate and false positive rate? Well, when x equals to y, what is that? It's a straight line that's going from diagonal to diagonal, right? So that's exactly why you have this line. Now, when would data go below this line? Well, if things are absolutely horrible. If you're getting more data identified as the wrong classification, meaning if you have 100 positives and 100 negative, but then of those 80 positives are classified as negatives and 80 negatives are classified as positives. I hope that makes sense. If bulk of your data is wrongly classified, then you start to see the curve go the other way, and then your AUC would be pretty horrible, right? So this is basically your ROC, and now let's look at a real life ROC curve. This is the one that we actually got from one of our runs. Again, we'll look at that in a true, with our own data in a minute. But the point that what is the best optimal threshold? By the way, why are we doing ROC curves? To actually figure out what is the optimal threshold, and this one that is the closest to the top left, right? So any data point that's closest to the top left is the optimal threshold. So in this case, this is the optimal threshold. And if you look at the accuracy, the overall accuracy may not be high, right? The overall accuracy is 0.84. In fact, if you pick something down here, the overall accuracy is probably 0.92. But that's not the optimal threshold, because an accuracy of 0.92 means true positives, you're getting 100% accuracy. But then what if you get only 70% accuracy on the negatives? That's not an ideal thing. You need to balance between these two. That's why this can be very useful to figure out what is that optimal threshold that gives you the right balance. Now, I learned this a while ago, but then I never figured out how the heck do I find that point? Well, you can look at all the data points and you can kind of trace it back, and there are some tricks. But one thing that I learned, again, let's jump into the code and I'll talk about how to get that data point in a second, okay? So let's jump to the code, and this is pretty much the same one from the last tutorial. Again, please watch that if you haven't. This is about binary classification, and I have a whole bunch of parasitized images and unparasitized images. So the parasites, they have like these type of dots in them, and the uninfected, they are pretty clean. And then I should have labeled the other way, but too late. I labeled my parasitized or infected ones with a value of 0. So when after the sigmoid, if I get a value close to 0, then that is parasitized, okay? And if I get a value close to 1, that means uninfected. Well, I wanted 1 because I don't want my images to show infection. That's the reason I added this one. Now, so, we are using the sigmoid activation for the last, layer, right? For the output layer. And it's outputting like one value, which is the probability. And I'm using binary cross entropy because this is a binary problem, and RMS. So let's actually redo this for 10 epochs, so we have some data to work with. Okay, so let's go ahead and run all of these lines, and I'll pause the video and then continue once that's done. Okay, it should be a few seconds anyway. Okay, it just took like 30-40 seconds. It's done. So now what do we do when we train something, right? We typically look at, okay, the validation loss and accuracy, but let's quickly test this on a couple of images. Okay, let's actually test this on an image 23, which I know is parasitized. So we need to get a value that's close to 0. So when I run these lines, look at the output. So there you see kind of barely, these two dots. And it says the prediction for this image is 0.64. The actual label for this image is 0. That means it's actually wrongly predicting. Well, the prediction is 0.6. If I set a threshold at 0.7 and anything above 0.7 is, belong to one class, and anything below 0.7 belongs to this class, then this is fine, right? Then this is great. But that's, again, this kind of helps us decide our threshold. So let's look at image number 26, actually 22, which is parasitized, and let's see if it is correctly doing it or not. And again, my notes here is for 300 epochs. Okay, so here again, 0.73, it is supposed to be close to 0. How about n equals to 24? Image number 24 should be uninfected, so I should have a value close to 1. So there you go. Well, this is a crappy model, I should say, which we'll find out from our confusion matrix. We only trained it for 10 epochs, so this is okay. So if you want to look at overall accuracy, let's go ahead and evaluate this on a whole bunch of test data. So it looks like the accuracy is about 61%. Not that good, actually. Yeah. Now, what is confusion matrix? And again, the way you kind of draw this confusion matrix is, or get this confusion matrix is, it's part of scikit-learn metrics, import confusion matrix. Okay. So this is part of scikit-learn metrics. Now I'm setting a threshold of 0.5 for now. Well, I'll set it down here. So first I'm predicting, right? We are getting our Y predictions, and I'm predicting them on my test data. And then I'm setting a threshold of greater than or equal to 0.5 for now. Okay. And then let's actually compare our predicted values and the test values, right? So this is how you generate a confusion matrix. Our confusion matrix, of course, we are importing this, and our confusion matrix is applied on the actual test, actual Y values that we have used, whether it is training or testing, yeah, actual Y values versus the predicted Y values. Remember, that's exactly what we kind of mentioned as part of right here. So these are actual values on the X and predicted values on the Y, right? So this is what we're trying to plot. So that's why we are importing these two. So let's go ahead and print the confusion matrix. I'll share the code so you don't have to worry about that. This is a crappy model. So the true positives, it's actually getting 43 images classified, and true negatives 79. So the model is doing better distinguishing true negatives, okay? And these are, again, what is the bottom left? False positives, 23, and false negatives, 55. Pretty bad model, we understand that, but the whole point is, okay, we know it's bad, but what is the right threshold to actually segment these into different categories? Okay, so let's go down to ROC. Now, I already mentioned about what ROC is, so let's not go through the text, but though, again, scikit-learn.metrics is a great library to actually for metrics, as it suggests. So we are going to import ROC curve from scikit-learn.metrics, and we'll do exactly the same thing again. We are going to predict the model right there. Now I'm not going to predict for a specific threshold, because that doesn't make sense for ROC. ROC is all about changing the thresholds and looking at the true positive, false positives, right? So it does change the threshold automatically. So now, based on the data that we actually have. So let's go ahead and do our Y prediction on all of our test data, okay? And then the way you apply this is ROC curves, just like your confusion matrix, Y test and Y prediction, okay? So that's exactly what we are doing here, and what it outputs is false positive rate, true positive rate, and the thresholds, corresponding thresholds. Okay, so let's run these lines first, so you can, and then we can plot it. Okay, so that's fine. So if I open my false positive rate, for example, thresholds, so these are all the thresholds that it actually tried. Okay, and then true positive rate is this, and false positive rate, you'll have something similar. Okay, so we have 84 data points. Apparently that's all the test data that we actually have. Okay, so let's go ahead and plot it, and I'm also plotting 0 to 1 line as our you know, the random line, right? So the random classifier, so we can kind of compare the plot. Okay, so let's go ahead and plot it and show it on the right hand side. So there you go. This is our plot. Not a great one, not a great ROC curve. Okay, so and if I want to pick a threshold, then the threshold would be like this one right there on the top left. Okay, and by the way, when we looked at our I think we should do this first. When we looked at our you know, confusion matrix, you see 43, 55, 23, 79. If I change my threshold to 0.7, for example, then that confusion matrix would change, because now our classification is changing. You see, now 75 true positives and 46 true negatives. If I change this to 0.8, then I think I made the point. You see, that is getting lower, but then this is getting higher. If I go the other way around, then I'll get like more of these top right and less of the top left. Okay, so let's go to 0.2 threshold, and then now we'll actually get more on the top right, and that's a very crappy one. It's doing 100% of these images correctly identified as true negatives, but then it's not doing good with positives. We know that because we saw one of the positive images, one of the parasitoid images, it's got a probability of 0.7, but it should be 0. Below 0.5. So if I actually do 0.8, then it actually does very good for these true positives, because we are actually getting very high numbers for those. Anyway, go ahead and study this on this data set. I'll share all the code and everything, so you can sit down and study it yourself. Let's stick with this, and we looked at, okay, I'll wrap this up in the next few minutes, I promise, but we looked at this curve. Let's also look at this curve for 300 epochs, because we did that yesterday. We saved the model, so we can we don't have to retrain it. We can load the model and we can look at it. Okay, but one other thing I also included as part of this code is how do I find the threshold of the best threshold right there? Well, the logic here is let's say the optimal cutoff point is where the true positive rate is high and the false positive rate is low. Yeah, true positive. We have to maximize this true positive and false negative, which means if I do TPR minus 1 minus FPR, false positive rate, then we should actually get this threshold. And that's exactly these lines. Again, I'll let you study these lines, but I'll share the code. But out of curiosity, what does it say? This one's saying that the ideal threshold is 0.63. So if I go back and set up 0.63 here, and then let's see if that has some sort of a balance. Yeah, it has a good balance between true positive, true negative, and also false positive, false negative. This is the reason why we need, well, ROC curve to visualize, but you can just use these lines to get the right optimal code. Now for this, what is the area underneath the curve? It's just part of, again, scikit-learn metrics. AUC is part of it, and again, it's using FPR, false positive and true positives, as inputs, because this is how we plot it, right? Our ROC curve, and it's given me 60.69, which means there's 69% chance that the model can distinguish between true positive and true negative. That's what this means. Okay, let's finish this by loading our existing model. So what I'm going to do is go ahead and use this from keras.models, import load model. I covered a video on how to load previous models again, and let's go ahead and load this malaria underscore model. This is our model for 300 epochs, and I hope this does much better than 10 epochs, right? So first of all, let's look at the accuracy. 84%, not bad. And let's just set a threshold of 0.5, because that's where I usually start. Have a look at that. Already looked very balanced, actually. So I think this is with these many epochs, it should do a pretty good job. And I changed my threshold to, yeah, that seems to be doing pretty good. Not much changing, even though I'm changing the threshold a lot. But let's see how the ROC curve looks like. Okay, so let's go ahead and plot the ROC curve. That's more like it. You see how it's moving more towards the top left? That means this model is much better than the previous model. Okay. So, and by the way, you can also use not just deep learning. If you want to compare this with, random forest, yeah, you can still do that. All it needs is your prediction, y predicted and y true, right? That's pretty much it. And finally, let's see let's actually look at what the area underneath curve is. It's 89.79% that it can actually get. It's a good model, actually. So based on that, so let's go ahead and find our ideal threshold. Ideal threshold is 0.908. So looks like it's a good model anyhow, with these many epochs. So let's see how the balanced result looks like. Pretty similar to other thresholds. 82 and 85, 16, and 17. Okay, so again, this got 25 minutes or so for this video, but I hope you found this to be very useful. And again, as usual, let's cover a different topic in the next video. And until then, please go ahead and subscribe to this channel, because I know you find this useful. If you stuck, if you watch this video for 25 minutes, I know you love this channel. So go ahead and subscribe it. Thank you very much.